1, and this is, let's say, nexus 2. You might have two interfaces, or you can have more than two interfaces, like you can have four interfaces here. And we can bundle all of these interfaces. So EtherChannel is supported by nexus switches. Manual and dynamic methods are available for making the configuration. So this is what we have discussed. This is just for a quick revision, and then we're going to start with our new topic, which is VPC, virtual port channel. So manual and dynamic methods are available for making the configuration. Please note that PAZP is not supported on nexus switches. PAZP is also a protocol. It is supported on our catalyst switches to make the configuration on our catalyst switches, the ether channel configuration. But in nexus switches, PAZP is not supported. Only LSCP and on mode supported on nexus switches. And as we have discussed that in case of LSCP, we have two options or two interface modes, active and passive. So first of all, we have seen that what is a spanning tree protocol on the nexus switches, how the spanning tree protocol is configured. After that, we have seen if you're running spanning tree protocol is going to block our redundant ports. It's going to block our redundant ports. So that's why now what we don't want to block any of the physical interface. Okay, makes sense. So we will bundle those interfaces, and a virtual interface will be created, and that virtual interface is known as port channel. That virtual interface is known as port channel. So this virtual port channel, sorry, this port channel will represent all of these physical interfaces. Now it appears that there's just only one interface, but technically we have four interfaces here. So all of these interfaces will be used to forward the traffic, but from the STP point of view, there's only one interface which STP can't block. Each interface, let's say you're bundling these interfaces, each interface is of gigabit Ethernet. It means that each interface is having the bandwidth of 1000 Mbps. So this time, if you bundle four interfaces, you will notice the bandwidth of this port channel interface is going to be 4000 Mbps, or you can say 4 Gbps. The collective bandwidth. So the port channel will show you the total bandwidth is 4000 Mbps, or you can say 4 Gbps. But as we have discussed in the last class, there's a problem with this. I can't say a problem, but we have a shortcoming on nexus switches or in this ether channel configuration. So ether channel allows us to make the configuration or the link bundling, but the problem is there's a very simple condition. Let's say if you're blocking, if you have this nexus 1, you have nexus 2, and you have nexus 3. So now my nexus 1 is connected with nexus 2 also, nexus 3 also. This time, if I have this type of connectivity, let's say, again in layer 2 mode, if we have, by default the interfaces are running in layer 2 mode, so we will be running a protocol STP, and STP will block one of the redundant ports. Let's say my nexus 2 is the root bridge. So even if this switch is elected as the root bridge, one of the interface will all of the interfaces are DP. Here we have RP. Let's say this interface is RP, this will become DP, and this port will become alternate. So as we have already discussed, the RP and DP will remain in the forwarding state, and the alternate port will remain in blocking state. The alternate port will remain in the blocking state. Now what I want to utilize all available physical interfaces, and in order to do that, I have to bundle these interfaces together. But the problem is, as per the rule of ether channel, the links you're gonna bundle together, they should be connected on the same switch. This would be connected to the same switch on the other side. This should be connected to the same switch on the other side. That's the problem with ether channel. Or we can't say problem, but this is the condition. This is the condition. And it applies to catalyst switches as well as nexus switches. As well as nexus switches. Even if you have the catalyst switches, you will see the same problem. You will see the same problem in catalyst switches. That is not our cup of tea, guys. We are not here to discuss about the catalyst switches, but here we have two solutions. If we talk about the nexus switches, if we talk about the nexus switches, let's say this is my nexus 1 again, and this is my nexus 2, and this is my nexus 3. They are connected with each other like this, let's say. And on this side, we have 3 catalyst switches. You can have 4, but let's just make it a simpler topology. This is my catalyst 1. This is my catalyst switch 2. And this is my catalyst switch 3. So we have 3 catalyst switches and they are connected like this. So in both cases, I'm running spanning tree protocol and spanning tree protocol is blocking the interface. So I want to avoid that situation. And in order to avoid that, I will be bundling the interfaces. I will be bundling the interfaces here. In order to bundle those interfaces, they must be connected to the same switch. But that's the concern here. So in case of nexus switches, we have a solution known as vPC, virtual port channel. Virtual port channel. And in these catalyst switches, we have a technology known as virtual switching system, or it is also known as stacking. It is also known as stacking, virtual switching system. So what this VPC is going to do in our nexus switches, using this VPC, I will combine these two switches also. Not physically, but virtually these two switches will appear as just one switch. The downstream switch, the nexus 1 will think that it is connected to the same switch on the other side. That's why we will be able to bundle these two interfaces together in the same port channel. In the same port channel. And on the other side, on the nexus 1, 2 and nexus 3, these interfaces will be bundled together. So on both sides, this is the physical view of the topology, but the logical view of topology will look like this. The logical view of the topology will look like this. This is my VPC switch, and then this is the nexus 1. So nexus 1 will think that it's connected to the same switch using two interfaces, so that we can bundle on this side also and on this side also. So this is going to be the physical view of the topology, and this is going to be the logical view of the topology. Likewise, in case of catalyst switches, we have this solution known as VSS, virtual switch stacking. Guys, it needs special attention, and we have to have special hardware also for this catalyst switches solution, the virtual switching system. In this case, we will create a stack of these switches, and for that stack we need a stacking cable also. Then they will also appear as just one switch. They'll also appear as just one switch, VSS, and then this is the catalyst 3. So they'll think, okay, now we are connected like this. So this is my VSS, let's say virtual switch system, and then this is our catalyst 3. So logically they'll appear as one, so we can bundle these interfaces together. And that's how we can do multiple things. First, we can avoid spanning tree protocol. We can't avoid the spanning tree protocol, but spanning tree protocol cannot block the interfaces. They'll just appear as one interface. Second, we are able to have the link level redundancy as well as the switch level redundancy. Even if one of the catalyst switch goes down, still we have the connectivity to catalyst 1. To the catalyst 1. So in Catalyst switches, we have VSS, and in Nexus switches, we have VPC, virtual port channel. But here, guys, our concern is VPC. In Catalyst switches, you might have seen it, but in Catalyst switches, we have dedicated stack port. Stack interfaces on Catalyst switches. They have special ports and they are always connected like this. First switch with the second, second with the third, third with the fourth, fourth with the fifth, and then the last one is connected again to the first switch. And the stack cable look like this. So in the back side or in the rear view, we will see the stack port. We will see the stack port. So we have dedicated interfaces on our Catalyst switches. And here, this is the first switch. Switch 1 going to switch 2. Switch 2 going to switch 3. Switch 3 going to switch 4. Switch 5, switch 6, switch 7, and switch 8. And then last switch is connected with the first switch. So it is a failure protection here. Like, let's say if one of the switch goes down, one of the switch is not working. If you haven't connected this cable, then the top two switches will be isolated from rest of the switches. But now we have the connectivity. So even if one of the switch is not working, still all of these switches, this 4, 5, 6, 7, 8, these switches are reachable to these two switches using this link. So that's why we always make sure that we connect the stack cable like this in a redundant manner, so that in case if one of the switch goes down, we still have the stack connectivity. This is known as VSS, guys, virtual switching system, or we also known as stacking. And we need a dedicated stack cable, dedicated stack cable for Catalyst switches. But in case of VPC, that's why in Nexus switches the VPC is more simpler as compared to the VSS, because in case of VPC we don't need special type of interfaces. The usual interfaces we have on the Nexus switches will be used for VPC, but this is the stack cable. On few switches this is the mode, but we have other connected type also in the stack cable. So that's how we will provide the stacking. Let's come back to our main topic of the day, which is VPC, virtual port channel. So we'll have the theory part first. We'll discuss about a lot of things. What is VPC? What kind of problems it is going to solve? The VPC components. Then what is the role of each and every component in VPC? After that, we'll see the configuration part also. So we have a topology here in which we have three Nexus switches. We have three Nexus switches. Two Nexus switches on the top and one Nexus switch in the bottom here. So what we will be doing here, Nexus 1 and Nexus 2, they will be becoming VPC peers. It means that we're going to configure VPC between these two Nexus switches. They will be building a VPC connection with each other. And then this Nexus OS 3 switch will be bundling these two interfaces together. So from this switch perspective, we will be having just one switch on the top. But first of all, let's see what is VPC and how it is going to solve the problem. So this is the thing I was talking to you guys. In VPC, this is my Nexus 1. This is my Nexus 2. And let's say this is our Nexus 3. So this is the physical connectivity we have at the moment. But if you look at this topology from the VPC perspective, this topology will look like this. The topology will look like this because both of these switches will appear as just one switch. They will appear as just one switch. So we will be able to bundle those interfaces together. What are the benefits of the VPC? A VPC allows links that are physically connected to two different Cisco nexus. It can be 7000 or 9000 series devices to appear as a single port channel to a third device. Okay. The third device can be a switch, server, or any other networking device that support link aggregation technologies. Because in data center networks, VPC is belongs to whom? The Nexus switches, and in Nexus switches we have connected the servers. So servers can be connected with multiple Nexus switches. Let's say this is my Nexus 1 on the top. This is my Nexus 2. Then we have the switches like access layer in traditional network. Likewise, here we call them leaf switches. Nexus 3, Nexus 4. So this time it is not just limited to the switches. We can have a server also, and this server is having multiple, the physical network interface card. So this server is connected with both in switches, the top level switches, the Nexus 3 and Nexus 4. So usually this one interface will act as active, and the other interface will act as standby. But if we do something and then these two switches will appear as one, then the server can have active connectivity, and it will be able to utilize both of the interfaces for data forwarding. So this VPC is not just limited to, between switches, it also support our servers or any other networking device that supports the link aggregation technologies. So the server supports NIC teaming. Now, once we configure the VPC, how it is going to help us to get more bandwidth in the network? First of all, eliminate spanning tree protocol STP blocked ports, because as we know that if the links are bundled, STP cannot block them. Uses all available uplink bandwidths. So we have two type of interfaces on the switches. The interface which is connected towards the end user. This interface is known as downlink. And these interfaces, this one and this one, they are known as uplinks. So if you are running the spanning tree protocol, then one of the interface will be blocked. But now if we bundle them together, I can also bundle these interfaces here, this and this together. But for that, I have to make sure that these two switches also appear as just one switch. Then I can bundle these two interfaces on this side and these two interfaces on this side. So STP will not be able to block any of the interfaces and will get full bandwidth here. Full bandwidth. That is also an advantage of using the VPC. Uses all available uplink bandwidth. Allows dual home servers to operate in active mode. Dual home means what? Dual home is a type of connectivity in which we have two links connected to two different devices. It is not just limited to the data center or Nexus switches. Even when we connect to the internet or the ISP, at that time also we use dual homed connectivities. Instead of just depending on one connection, we'll have two ISP connections. Likewise, we have dual home connectivity from this server to the Nexus switches. So then the server can have active links. Provides faster convergence upon link or a device failure. But for this, we'll discuss how it works. What is the keep live link? What is the you know the responsibilities of the keep live interfaces, keep live messages, and all. But here, in case if one of the link fails, then we'll start forwarding traffic to the another links. But we can also afford a node failure now. It's not just link failure. In normal ether channel, when we talk about normal ether channel, we have this limitation, right? And when we have this limitation, if this nexus goes down, we have the link level redundancy, but we don't have the device level redundancy. If nexus 2 goes down, my port channel will goes down. But in this case, if one of the switch goes down, still we have the another switch. So we have link level redundancy as well as we have device level redundancy here, as well as we have device level redundancy. Offer dual active default gateways. For servers, VPC also leverage native split horizon loop management provided by port channeling technology. So basically, this is the rule which we follow in normal ether channel also. Because if you notice, what do you think, guys? if I have bundled all these interfaces together, do we need spanning tree protocol here? Just think about spanning tree protocol. Don't think about VPC for a moment. Let's say I have this topology, these two switches, Nexus 1 and Nexus 2. The interfaces are bundled together. Do we need STP? What do you think?
No,
You said no. Yes. But the thing is,
no.
STP is still running. STP is still running in this topology. If this is a layer 2 port channel, STP is still running, because if all of the interfaces will be in the forwarding state, then still we have the chances of loop. How we will make sure that we don't have any loop in the topology? How we will make sure that we don't have any loop in the topology? So STP is still running. STP is still running here. STP is still running. The spanning tree protocol is still running in this network. What STP do? Let's say if Nexus 1 sends up traffic towards Nexus 2 using one of the interface. Now STP will make sure a frame received on one of the member interface will never be forwarded to any other member interface. That's why we still have STP running here. We still have STP running in this topology, even if you have bundled the interfaces together. Even if you have bundled the interfaces together, STP is still running in the network. Okay. Likewise, here in this topology, a packet entering a port channel cannot immediately exit the same port channel. This is the split horizon rule in the VPC, which help us to prevent the loops. So we still have the chances of loop, but we have rules also, and those rules will help us to avoid this. These are the architectural benefits of VPC. Simplified network design, build highly resilient and robust layer 2 network, because we have two types of redundancy. We have the link redundancy and we have device redundancy. Link level redundancy, and as well as we have device level redundancy here. As well as we have the device level redundancy. Enable seamless virtual machine mobility and server high availability clusters, because at the end of the day you are just connected to the same pair of switches. Scales available layer 2 bandwidth and increase bisectional bandwidth also. Grows the size of layer 2 network without compromising the bandwidth, because still we have the full bandwidth. None of the interface is blocked by a spanning tree protocol here. None of the interface is blocked by spanning tree protocol here. But we got some conditions, and the configuration is also involved, right? We have to make the configuration manually. Likewise, the ether channel, because even in the ether channel, if you notice, there are some compatibility requirements we need to fulfill, and those compatibility requirements are defined already. And if the devices are not compatible with each other, then there will be a problem. Okay, so we'll talk about this part is clear to everyone? Any question from this part? Please feel free to ask, or just give me a confirmation so that we can proceed next. Is this part clear? Why VPC? So the first question was why VPC is needed. Make sense?
Okay.
Hello.
Yeah.
All right. Let's see, guys. Next. VPC building blocks. VPC building blocks. You have to remember one thing about VPC. The Nexus switches, as we have discussed, the Nexus switches can be operating in one of the two modes. Either the Nexus switch is operating in NXOS mode, and the Nexus switches are operating in ACI OS mode. Nexus operating system, ACI operating system. In case of ACI operating system, we will be managing our Nexus switches through a controller known as APIC, Application Policy Infrastructure Controller. So there's a difference between the VPC configuration, guys. The configuration you are making on the Nexus OS switches or on the ACI OS switches. So you will see a difference. In ACI OS switches, we don't need all these components. But here, first of all, we are talking about the switches which are running in NXOS mode. So in case of NXOS mode, all of these components are playing a very important role. We have a lot of building blocks in this VPC. We have a lot of building blocks in this VPC. So first, we always start with this, let's say VPC components. So in VPC components, we have first VPC domain ID. We have VPC domain ID. VPC keep live link. VPC peers. VPC peer link. VPC member ports. VPC orphan ports. Then we have VPC orphan devices also. And then there's a protocol known as CFS, Cisco Fabric Services. So this protocol is known as CFS. This CFS protocol is playing a very important role in order to make sure that our VPC switches or the VPC peers have their configuration and the table is synchronized with each other. The tables are synchronized with each other. So the CFS protocol, also known as Cisco Fabric Services, is playing a very important role in our VPC. First of all, we have just a quick introduction. Then we'll explain it in detail. But first of all, if we look at this, we have VPC domain first of all. So now if you are going to bundle these two switches together, there's a domain ID. Like in case of OSPF, you're configuring OSPF. So two routers will have same area ID. If they don't have the area ID, they will not become member of each other, or the routing will not work. Likewise, if you want to bundle two switches together, you have to define there is a VPC domain ID, and the VPC domain ID should be identical. Let's say you say VPC domain ID 1, VPC domain ID 1. So at a time, a Nexus switch can be part of just one VPC domain. This is the first thing we define here. We'll discuss about this, the range and all. Then you notice between these two switches, I have connected interfaces. I've connected interfaces. So this interface is known as peer link. Then between the VPC peer switches, we have one more interface which is connected over layer 3 network. This interface is known as VPC peer keep live link. Then let's clean up this a bit. After that, you notice between this pair switches, we have a sign here, CFS, and arrow on both sides, right? It means that there's a protocol running between these two switches known as Cisco Fabric Services. Cisco Fabric Services. After that, this interface is going towards the downstream switch, and these interfaces are bundled together. So these interfaces are known as member port. These interfaces are known as member port. But there's one more interface, and this interface is not part of the VPC. This interface is not part of the VPC. So if this interface is not part of the VPC, it is known as orphan port. As its name suggests, orphan port. It is not part of the VPC, or it's not part of the port channel. That's why we call it an orphan port. And the device connected to this interface will be known as orphan device. A device connected with this interface is known as the orphan device. And this link is known as VPC, virtual port channel. If you look at this from this switch perspective, so for this switch, it is going to be a very simple interface known as normal port channel. It is a normal port channel. But for VPC peers, this is known as VPC port, virtual port channel. So on this side switch, we have the normal port channel, but on these sides, we have a virtual port channel, because the both interfaces does not belongs to the same switch, but they will appear as one switch here. Will appear as just one switch. So in VPC, we have all these components, and the components play a very important role here. And when we make the configuration, first of all, we always make sure that all of these components are there and the configuration is done properly. Okay, so first of all, if we talk about the VPC domain here, VPC domain. On the Nexus switches, we have a command here, show VPC, and on the show VPC domain, at the top, you will always see the domain ID. We'll talk about the peer status, keep live and all. But first of all, if you focus on this, we have a VPC domain ID 1 at the moment. You have a VPC domain ID 1. So now when we configure VPC here in the switches, the very first thing we define is the domain ID. And domain ID must be same on both switches. Switch 1 and switch 2, who are going to becomes the part of the VPC domain, the VPC domain ID must match. The VPC domain ID must match. So we'll discuss about these components here. Let's say first we have the VPC domain ID, right? So as its name suggests, group two Nexus switches into a single VPC domain. Then we have a range of this. Normally the range is 1 to 1000, because it's an range is 1 to 1000. Then please make sure that the domain ID must match on peer switches. So if you have two switches who are peer of each other in the VPC, the domain ID must match. The domain ID must match. Then domain ID must be unique within the network. You'll say, okay, you said that it should be same, but what does this means? Guys, we can have multi hierarchical VPC also, right? let's say you have this switches, switch 1, switch 2 here, then you have switch 3, switch 4. They're connected like this, right? And then my switch 1 and switch 2 is also connected to a server. Let's say this is a server, and the server is connected with switch 1, switch 2. So I want to utilize both interfaces, the connected on this switch. So I will create a vpc membership between these two switches. Then the problem is on top we have two separate switches. Then these interfaces needs to be bundled together. So you will do what? You will also create a VPC domain here. So in this case, make sure, let's say you are using a VPC domain ID here, VPC domain ID 100. So here you must use the VPC domain ID 200. But between these switches, on this it must be 200, and here it should be 200, 100 and 100. So it should match here, but it should be unique between two VPC domains. Two VPC domains. This is the first thing we need to define in VPC, the VPC domain ID. After this VPC domain ID, we have a VPC peer link. We have a VPC peer link. This is our nexus 1. This is our nexus 2. And then this is nexus 3. I'm just taking one switch in the bottom side, guys. Nexus 3. The connectivity is like this, right? And I want these two switches to appear as one. So they need some sort of communication with each other. It is like husband and wife, right? So they must have some sort of connectivity between them so that they can have some their own conversation related to VPC, not related to the user traffic, but related to the VPC. That's why we must have a VPC peer link. Now, what are the recommendations, guys? You can have just one interface, but there are some recommendations related to this VPC peer link. And whenever you will see any topology of VPC, like we were talking about this here, we were taking just an example. In this topology, you just see two interfaces. Whenever you will see a VPC design, you will always see two interfaces connected. Here also you see two interfaces connected as a peer link. So this is not a condition, okay? Don't think that it's a condition. It's just a recommendation that you must have two peer links to offer the redundancy, and they can be bundled together. This is a normal port channel. This is a normal port channel, okay? So what does this peer link do? As its name suggests, peer link. So when we were talking about the CFS protocol, Cisco Fabric Services Protocol, the Cisco Fabric Service Protocol is used to synchronize the tables and the information between these two switches together. So this VPC peer link synchronize layer 2 control plane info. Then peer link must be configured as a trunk port, because we have multiple VLANs conversation here. So that's why it is always, sorry, not recommended, but it's a condition that the peer link should be configured as a trunk port. Okay. CFS protocol is using peer link to share MAC address table ARP table, STP states, etc. Once we'll discuss about the CFS protocol, we'll see what kind of information it advertise between these two nexus switches. Because let's say if there's a user sending traffic outwards, right? So as per this nexus one, it will just load balance the traffic. So the first packet went to whom? The first packet went to nexus one. Nexus one will forward it further. But when the response is coming back, response is coming through nexus 2. But the problem is when this user was forwarding the traffic with MAC A, Nexus 1 will learn this MAC address. But when the response is coming through Nexus 2, the source MAC will become destination MAC. Nexus 2 will say, okay, I don't know anything about MAC A. Where is this MAC A is located? So it must be synchronized. The ARP table must be synchronized between these two Nexus switches. So that's why we have a dedicated protocol here, which is known as CFS. And the CFS messages are sent over the peer link. Recommended to connect minimum two links as peer link. Not a condition, always remember. So whenever you'll see a topology in books on internet, you will always see two interfaces peer link, but that's not a condition, guys. You can have just one interface as a peer link. Then peer link is supposed to having 10 Gbps of bandwidth. It is again a recommendation that the bandwidth should be at least 10 Gbps of one interface because they are actively communicating with each other. So we don't want any kind of latency between Nexus 1 and Nexus 2 related to the control plane information. That's why it is recommended to connect 10 Gbps interface between the VPC peer switches. Make sense, guys, till now? Any challenge here? Whenever you have any challenge, please feel free to ask, okay?
Okay.
But till now, I think it's clear.
Yes.
After this VPC peer link, we have VPC keep live link. VPC keep alive link. What that keep alive link is doing here? Playing a very important role. You want to guess, guys? Anybody want to guess?
It may be make sure that the peer VPC switch is alive or not.
As its name suggests, right? VPC keep alive link, or you can say VPC peer keep alive link. So this is a layer 3 interface, guys. The VPC peer links are layer 2 interfaces. The peer keep live link will check connectivity over an IP network. So we can have any layer 3 network, or the peer keep live link can also be directly connected. You do not have to connect it through any other router or any switch. They can still directly connect it with each other, and the interface needs to be configured as layer 3. So this is known as keep live link. And on this keep live link, we'll configure an IP address. We will be configuring an IP address. So as its name suggests, keep alive. There are timers. We'll discuss about those timers, like how frequently the peer keep live messages will be sent, what is the hold time, and all. Check the liveliness between two VPC peers. Check the liveliness between two VPC peers. Encapsulated with UDP. So the VPC keep alive message will be encapsulated with UDP here. Like this is the keep alive message. Okay. Then encapsulated with UDP, and after UDP we have the IP header. So UDP based message type. Then periodic message. Management interface is recommended for keep live. But again, it's not a condition. You can use any other layer 3 interface as a keep alive link, but it's all it's recommended that you must use the management interface. But it doesn't carry any traffic related to the VPC. Okay, it's just used as a keep live. So only keep live messages are being sent over the keep live link. The CFS protocol is still running over the peer link interfaces, guys. Likewise, if we go back to the diagram here, we have VPC domain, keep live link, VPC, peer link, sorry, VPC, peer link. So the Nexus one, this one, and this one, they will be known as VPC peers of each other. They'll be known as the VPC peers. Then you have the member ports. These interfaces will be bundled in a virtual port channel. And then we have the CFS protocol. Then we have the CFS protocol, Cisco Fabric Services protocol. Then we have the CFS protocol. All other things are, they give their explanation by the name itself, but we have the CFS protocol, which is playing a very important role in VPC. So this CFS stands for Cisco Fabric Services. Cisco Fabric Services. CFS. You'll say, okay, do we need to enable it? No, we don't need to enable it. It's by default enabled when we use the VPC. As its name suggests, it's a Cisco proprietary protocol. By default, it is enabled on VPC peer links. Then it is responsible to synchronize configuration and state between VPC peer switches. VPC peer switches. The VPC domain configuration, port channel configuration, VLAN, spanning tree settings, right? Then it also exchanges the related information, the MAC address table, the LSCP states, VPC member port status. Then like I said, the VPC domain ID must be same between two switches. Who will check this? The CFS. The CFS. Okay. And you cannot manually disable CFS for VPC. You cannot disable this. Whenever you'll run the command feature VPC, when we go to the nexus switches and we say feature VPC, once you run that command, CFS protocol will be enabled and you can't disable it explicitly, or you can't say, okay, I don't want to run CFS. As long as you're running the VPC, the CFS protocol will be there. It doesn't deal with the user traffic. It has nothing to do with the user traffic. It only works with the nexus peer switches. Only advertise the information related to the MAC address, related to the configuration changes, spanning tree protocol, and all. So this is my nexus 1. This is my nexus 2. And then we are configuring VPC here. So this is the peer link. So over this peer link, the the CFS messages will be sent. Cisco Fabric Services and Cisco Fabric Services. It has nothing to do with the user traffic. User traffic will be forwarded using the member ports. Using the member ports. This is also a very important component of our VPC. We'll discuss about the rest of the part also, the consistency check and all. So we have peer link member ports, the interfaces or the switch ports which will be bundled together and they'll become part of the VPC. Orphan port connected to non-VPC interfaces are known as the orphan ports, and the devices connected to non-VPC interfaces are known as orphan devices. So let's say in this case we have one orphan port which is going towards the orphan device. Yes, guys. Now you can ask me, please. Feel free to ask from this particular slide, the VPC building blocks. Any challenge till now?
No, but the communication between the Nexus 1 and the Nexus 2, which we have in the VPC domain, same domain. So the communication should be happening through other links. Uh, is that link you mentioned as the member link, member interface?
What kind of communication you're talking about?
I am talking about the two Nexus switches which we are configuring in the same VPC domain, right? The switch one and two.
That communication is over the peer link. That's why we have this dedicated interface.
Okay, that is VPC communication. So let's
Yes.
say we have a host connected on the Nexus switch one, and that host wants to connect to the another host on the Nexus two. So how does that communication happen? Is that over other links like
Through the port channel, yes.
that? Is that the links you are calling the member links or something?
Yeah.
Or
So see, the VPC peer link will never be used for user traffic. So whenever it comes to the user traffic, it will be forwarded through the rest of the interfaces. But this peer link will never be used to forward the user traffic here. Okay.
okay.
Yeah.
Also, okay. Also, we have orphan port and orphan devices. So, uh, is there anything relevance of that interfaces in the VPC?
No, they just want to show us here one thing, that it is not required to configure each and every interface in VPC. You can have the interfaces which are not part of the VPC member ports. That's what they are trying to convey here using this
Okay,
orphan port. That if you have the downlink interface, it should not be part of, like, it is not mandatory to configure them in a VPC. They can be standalone interface also.
okay, yeah,
Okay.
okay.
All right. I hope you guys enjoying it till now. Let's proceed next. Here, this is a very basic command on the switches. Either you have the spine switch or the leaf switches. They have this command show VPC. The command show VPC. So in this show VPC option, we have this VPC domain ID, which is 1. VPC peer status, peer link is not configured. Configuration consistency check, per VLAN consistency check will come to this part. Then we have VPC role. Right, none is established because this configuration is still not done when we took this screenshot. But this screenshot is just to show us that the domain ID is configured on the top of it, the VPC domain ID 1. So these are the building blocks of VPC, guys. Very important. After that, VPC can be of two types: single-sided VPC and double-sided VPC. D is not looking like D. Let's draw it again. D. Sorry. Double-sided VPC, virtual port channel. So in case of single-sided VPC, you notice this is a downstream switches. Even this is a server. So now these two switches are bundled together and they are acting as a VPC domain. So let's say domain ID 1, domain ID 1. This is known as single-sided VPC. Only on one side we have the VPC. So these interfaces, they will be bundled together. So we will call it virtual port channel. What we will call it? Virtual port channel. But the interface is bundled on this side. They are simple port channel, nothing special. Port channel, normal port channel. This is the simple port channel, single-sided VPC. Then we have double-sided VPC. In case of double-sided VPC, you see that they're bundled. Then here also we have the VPC, and that's why we're saying VPC domain ID must be unique between these two domains. So domain ID 1, domain ID 2, let's say. Okay. So this is known as double-sided VPC. In this, we have port channel on both sides. We have port channel on both sides. All right. Then consistency check or configuration compatibility check, you can say. When we bundle interfaces together in a normal port channel, let's not talk about the VPC, but when we have the normal port channel, then there are some compatibility metrics, or you can say they must be having some common properties. So this is my switch 1, switch 2. If I have 4 interfaces between them, then there are certain conditions, right? If I'm bundling them, duplex must match, speed must match of all these switch ports, interface type must match, either access or trunk. So if you're bundling four interfaces, you can't have two interfaces as access and two interfaces as trunk. All of them, either they must be trunk or they must be access port. If access ports must be assigned to the same VLAN. If you have these four interfaces together, you want to bundle them. This is interface 10, VLAN 10, VLAN 10, VLAN 10, VLAN 20. You can't bundle all these four interfaces together. If they are the access port, the fourth interface should also be part of VLAN 10. Otherwise, it will be isolated or suspended. So if access port must be assigned to the same VLAN. If you're bundling the trunk port, if trunk ports, the allowed VLAN list must be identical. So all of these interfaces are trunk. Then if you allow the VLAN, because we can modify the allowed VLAN list, so the allowed VLAN list must be identical on all the trunk ports. Likewise, we have consistency check in VPC also, or you can say the configuration check. If they don't match, we have two types of consistency check. Let's say we have critical consistency check. If they do not match, the VPC is suspended to prevent loops or corruptions. So these parameters must match exactly between both peers. Global VPC parameters like VPC domain ID, role priority, VPC keep live status, STP settings, spanning tree mode, RSTP, MSTP, or breeze ID, port channel settings, LSCP modes, or hashing algorithm, interface parameters, VLAN allowed list, MTU, trunk, native, VLAN, and all. VLAN configuration must match. VPC system or system priority must match for proper LSCP negotiation. These are the critical parameters. Then we have non-critical consistency checks also. If this differs, VPC stays up, but traffic might behave inconsistently. So we are not, you know, forced to match these parameters, but if they match, great. Like interface settings, quality of service, class of service, flow control, description of the interface, IGMP snooping or multicast, port security, storm control, STP timers and STP features, VLAN membership, non-VPC VLANs, like the orphan ports. So these things can differ. Okay, they are not critical parameters. If they match, great. Otherwise, there is no certain conditions that they must match. Otherwise, the VPC will not work. VPC will work even if these settings will not match. How we can check it? You go to the VPC switches and there's a dedicated command for given to us. Show VPC consistency parameters global. Using this command, we can check the things. They must match. Type 1, VPC will be suspended in case of mismatch. That's why we have this categorization. Type 1 consistency check, type 2 consistency check. So type 1 is considered as critical consistency check, while type 2 is considered as non-critical consistency check. Considered as non-critical consistency check. Once you match all this, you can start the configurations. But before making configurations, please take care of few things. First, verify prerequisites. NXOS version, connectivity, licensing. The VPC must be supported. Nowadays, if you talk about Nexus switches, all iOS or all NXOS versions support this VPC features, connectivity and licensing. After that, you will enable required features. Because in Nexus switches, even if you want to configure OSPF, or in the last class, guys, we were configuring LSCP. So you remember, we go to the configuration mode and we say first feature LSCP. If you were running the commands without this feature LSCP command, we were getting an error message that okay, first go and enable the feature. So we'll say feature LSCP. Even in case of VPC, you have to enable LSCP here, because for the link bundling, we're still using LSCP or on mode. So even if you're using the VPC, we're going to enable the LSCP feature. Then you'll say feature VPC, right here, feature LSCP, feature VPC, then feature interface VLAN. Now this feature interface VLAN is not mandatory. Feature VLAN interface. You need to enable this feature interface VLAN if using an SVI as a, if you're creating a switch virtual interface to use as a keepalive link, then you must enable feature VLAN interface also. You must enable feature VLAN interface as well. Then you will be able to make the further configuration on this nexus switches related to these VPC. First thing first, enable the feature. Configure VPC domain and role priority. Configure VPC peer keep live link. Configure VPC peer link. L2 port channel with trunking. Configure VPC member port channel, the downstream interfaces, and then you can verify the configuration. After verifying the configuration, you can save it, like copy running to startup, then save the configuration. But before that, you can verify it using show VPC brief or show VPC consistency check command. Show VPC consistency parameters. But before going towards this configuration part, let's talk about the primary and secondary LSCP also. The primary and secondary LSCP. Yes. So we have a topology in which we have two switches which are peer of each other and they are configured in the same VPC domain, Nexus 1 and Nexus 2. And then we have this Nexus 3, let's say. But now, right now, our focus is on something else. Peer link. And then these two switches are VPC member. VPC switch 1 and VPC switch 2. So in one VPC switch or one VPC domain, we can have just two switches, guys. In one VPC domain, you can have two switches. So domain ID 10. Here also we have the domain ID, let's say 10. Then in between these two switches, one of the switch will be acted as primary and second switch will be acted as secondary. So we have primary and secondary option in VPC, primary and secondary option in VPC. Even we have a dedicated command show VPC role to check this. Show VPC role to check the role of a switch. The role switch is primary or secondary. So learn about STP. I gave you a quick introduction in the last class also. So in spanning tree protocol, we have root bridge election. one of the switch will be acted as root bridge and rest of the switches will be known as non-root switches. Okay, so here we have two roles: VPC role primary and VPC role secondary. So first of all, the primary election. VPC primary election. The VPC primary election is based on two things.
Sorry, I don't have an answer.
Oh, sorry guys, it was election. So VPC primary election is based on two parameters, guys, similar to a root bridge election. Okay, the first parameter is VPC switch priority. Similar to spanning tree protocol, we have default value. Default priority is 32667. Default priority is 32667. But lower is better. Simple rule. Lower value means higher priority. So Nexus 1 in this case has a priority 32667. Here also the priority is 32667. Let's say if I make it 32665 here, so Nexus 1 will become the primary. But by default it's 32667 on both of them. Then what is the second criteria? Lower value is equal to higher priority, guys. Second criteria is the MAC address, or you can say the tiebreaker. The tiebreaker is the MAC address. The switch having the lowest MAC address will be elected as the VPC primary. VPC primary will be the Why do we need the primary switch? Any guesses here? Want to guess, guys? Why do we need the primary switch? Why do we need to elect this?
Uh, the same the same consideration as the STP, focal point of network.
Yes.
So we could,
So we have these two switches, but logically, we want them to act as one. So the primary switch will take care of the control plane data. You'll say, can we manipulate this election? Yes, we can manipulate the election. But if once we have a VPC primary, that will remain the VPC primary. VPC primary switch is elected to manage control plane functions like sending BPDU. So now you have two switches, but they if they'll send a separate BPDU, then the bottom switch will detect, okay, I'm not connected to just one switch. I'm connected to two switches because I'm receiving two BPDs with different bridge IDs. So there will be a conflict. So VPC primary switch is elected to manage control plane functions. Then both primary and secondary switches will be forwarding data traffic. So from the user traffic perspective, both of them are acting as active means they'll forward the user traffic. Both of them, they just primary is to handle the configuration validations and ensure both VPC peers are synchronized, right? And in case if the primary switch fails, the secondary switch will take over the role of primary. Take over the role of primary. So both switches will actively forward the user traffic, but control plane functions depend on the primary. In one VPC domain, we cannot have two primaries. Otherwise, this will be known as split brain conditions. Secondary monitors the primary and take over automatically if needed, because we have the peer link as well as we have the peer keep live link. So in case if the secondary switch detects that the primary switch is no longer active, so the secondary switch will take over the role of primary. The secondary switch will take over the role of primary here. Command to change the priority. So you go to the configuration mode. In the configuration mode, you go to VPC domain, the domain ID. Okay, then role, priority, and you'll put the value here. You'll put the value here, whatever priority you want to configure. But lower priority is better. Lower priority is better. So that's how we can change the priority of our switches here. In the Nexus switches, the VPC priority can be changed very easily using this very simple command. Using this very simple command here, we can change the priority, and that's how we can also manipulate the role. Cisco Fabric services, then primary and secondary. Okay. So whenever we make the configuration here, either you go to the spine. This is not dependent on spine or leaf. It's just the switch. Okay. So if we have the switch, you go to the switch first of all and you enable the feature using this command, feature VPC. Enable this command, feature VPC, virtual port channel. Virtual port channel. Then you define the VPC domain ID. And VPC domain ID, let's say we have defined one. This is not mandatory, guys. This command is not mandatory, okay? But you can change the role priority if you want. You can change the role priority if you want, but this command is not mandatory here. After that, we go to the switch again. You go inside the VPC domain. You configure peer keep alive destination IP address. because you will be sending layer 3 packets. But to whom? You will send the layer 3 packets to this IP address this time. So this spine switch will have a source IP, and the keep live messages will be sent to this destination IP. But we also have option to change the source IP here. Next to this, you have the option to define the source IP, because by default for the keep live we are using the management interface. But let's say you want to use other interfaces. You don't want to use the management. If you want to use other interfaces, what you will do in that case, you can change the source IP address. You can just say source, and then you can define the source IP address here, that this is the source IP I want you to use. So any other IP than the management interface can be used as source here. But by default, if you don't give the source IP, it will consider the management interface to be used as source of the keep live messages. Source of the keep live messages. Then after that, you say configure interface Ethernet 1/1. So we're talking about this topology. This is the reference topology here. In this topology, we have interfaces Ethernet 1/2, Ethernet 1/3, Ethernet 1/2, and Ethernet 1/3. And we have Ethernet 1/1. What is this Ethernet 1/1? This Ethernet 1/1 is the peer link. This is the peer link, and this is the keep live link. Like I said, guys, in most of the topology, you will see that in peer link we have two interfaces, but it's not a condition. It just the recommendations, but you can just have one interface as a peer link. In this particular topology, we have just one interface used as a peer link. That's also a possibility, and there will be no problem. But to have the better redundancy, it is recommended. Peer link, one keep live link. So now first I'll configure the peer link. In order to configure the peer link, we'll go to the interface Ethernet 1/1, no shutdown, channel group 100 mode active, interface port channel 100. And as we have discussed that this interface must be configured as trunk. You will configure that trunk, but still this interface is not configured as peer link. You have to specify it here. Switch port mode trunk. Then I said interface port channel 100 vpc peer link. So this command will define that this interface is going to be the peer link. This command will decide that this interface is going to be the peer link here. That's how we will make this configuration. First, domain ID. Then if you want to change the priority, you can change it. Otherwise, you can define the peer keep live. After peer keep live, you will configure the peer link. Then this interface Ethernet 1/2 on spine A and Ethernet 1/3 on spine B. They're going to be bundled in VPC. So on spine 1, you will go to interface Ethernet 1/2, no shutdown, channel group 1 mode active, interface port channel 1, switch port, trunk, allowed VLAN 10. Allowed VLAN 10. But still it is just a normal interface, normal port channel. But you have to go to this port channel, interface port channel, and you have to say VPC 1. After that, it will become the virtual port channel. Likewise, on this spine B, instead of 1/2, it will be 1/3. Now, guys, in most cases, just to avoid the confusion, they'll recommend to you that please use the same interface number 1/2 on this side also. If you're using Ethernet 1/2 as a member port on this side, use Ethernet 1/2 as member port on this side switch as well. But it's not a condition again. You can have Ethernet 1/2 on this side, Ethernet 1/3. But what should match? There's something which should match between these, right? First, the protocol must match. You can notice that on spine 1, I set channel group 1 mode active. It means I'm using LSCP. So you can't use on mode on spine 2. Second, the port channel number must match. This one, port channel 1. So on the other side, it should be port channel 1. And then VPC number must be identical. The VPC number must be identical. These things must match between these two switches, but the interfaces, the physical interfaces can be different, like Ethernet 1/2 or Ethernet 1/3. No problem in that. There's no problem in that.
Hello, sir.
Yes.
Actually, the spine A, like when we are configuring the this port channel, so it is showing spine A like one switch. So on another side, we have to configure on spine B, na another switch, the interface port channel.
Yes. Right.
But in below it is written spine A and spine A only.
The configuration is for spine A. The same thing goes for spine B. Only the switch will change.
Okay.
Okay.
For spine B also there in notes it is written.
Yeah. See, here we are talking about the configuration. The configuration will remain identical. Only the interface is gonna change here.
Will be
Instead of 1
changed.
slash 2, it's 1 slash 3. But rest
Okay.
of the configuration is identical.
Okay. Okay.
Let's say if you're talking about feature VPC, so you're doing it on spine 1. Likewise, you'll go to spine B and you will say
Feature
feature
VPC.
VPC.
Okay.
VPC domain 1. Then priority, here 10, on there you can configure 20. Keep
Okay.
live, this IP will change. For
Hmm.
VPC for spine 2, let's say in this topology, the IP address here on the keep live is 10.10.10.11, and here the 10.10.10.12, let's say. So for
Hmm.
spine A, destination will be this, and for spine B, destination will be this
This
IP.
one. Here the priority which we have set, it is the lowest one will be acted as a master. Correct, na?
Lower is preferred, yes.
Okay. Okay.
Okay, makes sense.
Yes.
So that's how we can make the configuration here. So you can notice the logical port channel ID must match on both peers. VPC number must match. It's not the VPC number 20 must be the same on both peers. Physical port numbers can differ, like Ethernet 1/2 here, but it can be Ethernet 1/3. VLAN trunking and LSCP mode must match across both the peers. Because now we are not making the configuration on individual interfaces. Once we'll bundle them, and then we will be changing the configuration for whole port channel, not just the physical interface, but we'll change it for the port channel itself. So the configuration will be applied to Ethernet 1/3 and 1/2, because now we will be making configuration on this VPC port, not on the physical interfaces. Okay, guys, make sense till now? Any challenge here? Please feel free to ask till now. Okay. So we will wrap up here today, guys, because in 20 minutes we'll not be able to make the configuration. It will take longer. So the configuration part will be covered in next class. Okay.
Okay. Yeah.
If you like this training, please join tomorrow also. And if there's someone join today, you can just talk to the management. Okay, for the classes, like how you can attend the further classes or for the enrollment. And let's connect tomorrow, guys. Then I hope you guys have enjoyed the session.
Yeah.
Sir, we are going to do practical for this
Yeah.
also.
Yes. We'll make the
Okay.
configuration as well. Okay.
Okay. Thank you.
Okay.
You're welcome, guys. Have a good evening. Bye bye.
Thank you. Bye.